dear participants, dear friends, who are here in our 5th meeting of our colloquium on portable X-ray fluorescence that is organized by the Global PXRF Network and the European Academy of Science and Arts, the STEMAC expert group, STEM in Arts and Culture. For our academy, this is a follow-up on a specialized section of the successful colloquia Arts Meets Science. We would like to invite you to contact us to present your own topics also, if you like, that you are dealing with in your activities on one of these coming colloquia. Myself and Michaela, who is now in Australia, and the time is not available, and appropriate for her to be present, wish to express our gratitude to Keelie, who is here, and to Doris Klida from the Academy office for their immense technical help in organizing the colloquia. Today we have one speaker, Professor Dr. Detlef Wilke, management and consulting company, who will speak on large-scale applications of XRF for ceramic provenance, given in 2 parts. One part focuses actually on calibration issues, which is and the most important, I think, of all. A couple of questions after the first part and more discussion at the end of this part. I would like to say a few words about our this evening speaker. Detlef Wilke is microbiologist, biotechnologist by education, and he has a long-lasting interest in cultural anthropology and archaeological theory. Since the 2000s, and after he kept an eye on non-destructive XRF analysis as a potential tool for overcoming the limits of mere form stylistic provenance attributions in archaeology and art history. His company provides contract analytics, calibration support, and data processing for ceramic provenancing for an international basis. Dear Detlef, the online podium is yours.
Thank you very much, Ioannis. But I'm not a professor. That means I have no teaching career in university. Well, hello, everybody. Thanks for having me, and thanks for giving me the opportunity to present my calibration approach for geochemical pottery provenance. This is the topic of the first part of my presentation. In the second part, I want to present some concrete examples of geochemical pottery characterization which go beyond simple identification of sources and trade routes of utilitarian and luxury ceramics. The pink dots on the map show the waster finds, which I have analyzed together with my colleagues in archaeology. The blue dots refer to settlement finds, mainly excavated in urban, rural contexts, in castles and abbeys, most of them devastated since centuries. The sample size per dot varies from about 50 up to more than 1,000, depending on the research task and the availability of sherds. In total, the map covers more than 20,000 samples analyzed between 2013 and today. There are some hot spots and many empty areas. The hot spots are often extended production districts where pottery was produced for export, which means beyond the demand of the local population. Provenancing of specialty ceramics like decorated pottery, stoneware, or refractory ceramics for metalworking, presumably traded over hundreds of kilometers, is of course of high interest to the archaeologists. During the past 20 years, certainly more than 1,000 papers have been published in English-speaking journals releasing non-destructive XRF data on archaeological find material. I guess that a considerable portion of these papers presented the results of stand-alone projects, and are rarely used as databases by other scholars. In such cases, data quality, accuracy, and methodological stringency may not be as decisive, but the qualitative results for qualitative evaluation of the study material. This is different in provenancing of obsidian and stone tools, but particularly of pottery as a major archaeological find category in many regions of the world. Leaving apart the old debates, I want to present my personal view on what is essential for ceramic provenancing. Non-destructive sampling is first. This is the precondition for selecting the analytical method. I take the term non-destructive literally. Fresh cuts or breaks are destructive. Data and instrument compatibility is essential. Without proper cross-calibration of instruments, data usage over time is impossible. Non-destructive sampling allows for high throughput, which is necessary to characterize large assemblages of archaeological find material with reasonable effort. From my perspective, rigid criteria need to be applied for the attribution of unknowns to empirically established clusters, namely either identity or distinctiveness. In case of pottery with hundreds of still unidentified potting sites in an extended region, mere similarity to a known cluster is not sufficient. For the same reason, the resulting inference from matching of the unknown sample with or differing from a certain compositional pattern is a plausible provenance hypothesis, but not a proof. This is an important message to be communicated to the sponsors, the archaeologists, and cultural heritage curators. These are the brands we were working with. Under operation, the window area must be protected by a lead cover. Special measures for radiation protection must be taken when large objects are analyzed. Whereas the number of obsidian outcrops worldwide is manageable, the number of potential clay pits for potting is almost infinite. Furthermore, volcanic glass is reasonably homogeneous, whereas clay sediments with or without intentional tempering are micro-heterogeneous mixtures of clay minerals and accessory components. Thus, we are faced with hundreds of potential raw material sources in a region, but with low inter-site differentiation and high intra-site variation, which is a direct consequence of the local sedimentation processes. Cluster similarity and overlapping is therefore the rule and not the exception. The left graph is a biplot of waste material from 4 medieval potting villages at the Cologne-Bonn promontory. Each of them at a distance of a few kilometers only. The right plot shows the cluster of Pinkstoff where one of these 4 villages, which has been traded up and downstream the River Rhine and which is found together with local South Hesse mica ware in the Frankfurt region, some 150 kilometers south of Pinkstoff. The question was therefore whether the 8 discriminative elements successfully used in XRF studies of obsidians would be sufficient at all for ceramic provenancing. The answer is quite often, but not always, and depending on the clays. Instrument calibration and validation is crucial when data shall be used, which necessarily have been established over extended times and by different laboratories or with different methods. XRF raw data calibration is complex, and non-destructive pottery analysis adds additional levels of complexity. Using a larger sample of geochemical reference materials for calibration and validation, some elements are quite good with coefficients of determination of the regression lines above 0.97. Others are really poor. These are zirconium and the low abundance trace elements gallium, yttrium, and niobium, which we all need for provenancing of pottery. One source of uncertainty are the recommended values of the certified reference materials itself, as for example in the case of zirconium. If plotted against the net counts, that means prior to any calibration, the figures scatter a lot, and the Excel regression line does not cross zero. For sure, matrix effects play a major role, but even for a single standard like NIST 2710, zirconium values considerably scatter with independent analysis. Alice Hunt has compared NAA, wavelengths, dispersive and energy dispersive stationary XRF at Mo and at the Atlanta laboratory and confirmed the scatter observed by the GeoRem collection at the Max Planck Institute for Chemistry in Mainz. For whatever reason, the NAA value for zirconium was particularly high. Interlaboratory calibration differences are ubiquitous and make the use of cross-laboratory data difficult or even impossible. Here's an example of Roman scherts from Ormels-Weißenturm near Koblenz. I wanted to provenance outlier scherts found in a Roman Vesta complex in Worms without having respective reference material from the location downstream of the Rhine. The Ormels-Weißenturm material exhibits a niobium anomaly, most probably due to volcanic weathering compounds in the nearby Mülheim-Keelie clay deposits. Indeed, the clay samples I took there make it very likely that the Worms Vesta scherts are settlement debris derived from Ormels-Weißenturm. However, I additionally asked for data from Wennigsen at Römisch-Germanisches Zentralmuseum Mainz and from Susanne Biegert at Gerwulf Schneider's former laboratory at Freie Universität Berlin. Both data sets with local scherts were analyzed with wavelengths dispersive XRF. As we can see, the three data sets are shifted from lower to higher zirconium and/or niobium concentrations. This is obviously due to calibration differences, but we cannot allocate the discrepancy to either of the two elements. Since the schirt samples are different, conversion factors cannot be calculated. As meanwhile, neither of the three instruments is still in operation, and in its original configuration, respectively, a cross-validation with a set of identical reference materials was also no longer possible. In an 8-dimensional rotation, the three data sets are very similar and partially overlap, but without prior knowledge, they could also be interpreted as resembling three different clay deposits or production sites. Thus, data sets used as archaeological reference groups need to be accurate as respect to reliable mass fraction values in the geochemical reference materials used for calibration. Since I was not satisfied with the validation of the geochemical factory calibration of my first Bruker instrument, which was an empirical calibration based on mudstone samples, I prepared fired clay blocks spiked with 8 discriminative elements, and later on also with calcium, which is needed for calcium-rich clays and loams and for correction of photon absorption of other elements by calcium. The concept of spiking is known as standard addition procedure, but has not been systematically applied to produce reliable geochemical calibration sets for relevant minor and trace elements. I ordered 200 kilograms of industrially processed Westerwald clay powder with particle size smaller than 63 micrometer and checked the bags randomly for homogeneity. When I prepared batches, then I prepared batches of each about 1 kilogram of clay powder spiked with each 4 aliquots of the respective discriminative element, which means a total of 32 spiked batches plus the blank clay. The element weights were sigma Aldrich analytical quality chemicals with 99% purity, which had to be homogeneously distributed in the respective 1 kilogram clay batch. The wetted, carefully worked paste was then divided into about 60 small blocks, dried, polished on 2 opposite sides, and fired at 800 to 850 centigrade for 2 hours. Perfect distribution of each spiking aliquot in the 1 kilogram batch was essential. Homogeneous distribution in the paste was checked for net count variation of the spiked element in each batch. If outliers were recognized, the batch was discarded. The zirconium base load in the Westerwald blank has been determined at 315 ppm, which is the crossing of the negative y-axis when the spiking aliquots are plotted against the net counts. The 4 zirconium aliquots cover a total range of up to 1000 ppm. The regression line properly hits the intercept. The slope of the regression line provides the calibration factor, the multiplier for converting net counts into mass fractions. The quality of the spiking set is obvious. The regression line has a coefficient of determination of 0.999 and a standard error of plus minus 6 ppm, reflecting the precision of weighing and mixing of the spiked aliquots and fitting much better than the individual certified geological reference samples. The spiking set confirms the order of magnitude of the reference material, but is much more precise. The regression line confirms that the lower concentration range of the Bruker mudstone series is reliable, whereas many of the certified reference materials scatter around the spiking line. The reason may be multifactorial, but explains why calibration discrepancies occur if only a small set of reference materials is used for calibration and validation, respectively. The 8 spiking sets have been analyzed in a collaborative project by Philipp Schulte at Technical University of Aachen with stationary EDXRF using pressed pellets. The instrument has its own independent calibration with a set of certified reference materials. The y-axis provides the values measured with the stationary instrument, the x-axis the given or expected values of the respective blank concentration plus the spiking aliquots. All correlation lines confirm the precision of weighing and mixing. 4 elements, iron, gallium, yttrium, and zirconium, with slopes of the correlation line between 0.95 and 101, exhibit an almost perfect agreement, whereas the remaining 4 elements somewhat differ. Titanium is overrepresented by 14%, rubidium is underrepresented by 8%, strontium by 10%, and niobium by 11%. The easiest explanation of these modest discrepancies is a selection of certified reference materials at the Aachen laboratory and the resulting calibration factors. In a collaborative project with Patrick Quinn, we first checked the calibration of an Olympus Delta instrument with the spiked samples and afterwards worked in parallel with a total of 3 different but identically calibrated devices. The Delta uses a fundamental parameter calibration. Gallium and niobium were not included in the FP calibration. The iron series gave slightly lower values than expected, but the regression line surprisingly was nonlinear. Only as a polynomial curve it crossed the intersect. The factory calibration did not correct for enhancement of titanium by increasing iron concentrations. The titanium values itself, that means in the presence of a constant iron background, however, showed perfect correlation, as well as the rubidium and strontium values. Only rubidium is shown here. The slope of the correlation line is close to 1. By contrast, yttrium was overreported by 16% and zirconium by surprising 35%. Thus, any interlaboratory use of concentration figures without proper cross-calibration and validation may be challenging. It is important to recognize that calibration concerns each individual instrument. Indeed, manufacturers may have improved the software, particularly when launching new models with improved detector performance. The spiking sets not only provide accurate calibration factors per element, but also allow for checking proper absorption, enhancement, and interference correction by the deconvolution software. Here, ARTAX-7 is used, which is a demonstration software distributed by Bruker for free. The actually licensed version is ARTAX-8. However, I continue to use ARTAX-7 because it is more stable on my computers. The amount of net counts per element recovered by the detector strongly depends on the composition of the sample material, its matrix. The matrix with its dominant major elements exhibits different scales of photon absorption of minor and trace elements. For example, the same amount of zirconium due to absorption by matrix elements will give significantly different net counts in a metal-dominated background than in an aluminum silicate or calcium carbonate matrix. Calibration factors for individual elements therefore strongly depend on the matrix the reference materials are based on. The deconvolution software typically does not specifically correct for matrix effects, but applies a generalized matrix correction by ratioing to the Compton scatter. In pottery, which means in a clay and sand-based type of ceramics, the elements oxygen, silicon, and aluminum contribute more than 85% of the mass, often more than 90%. The three elements together have an almost identical low mass absorption coefficient as regarding to the mid-set trace elements of interest. When using a clay matrix for spiking, the major variable element, which still remains causing matrix effects by absorption or enhancement, is iron. With increasing iron concentrations, the net counts of the elements with atomic number higher than iron received by the detector decrease, here shown for zirconium. Since natural clays and pottery cover a broad range of iron concentrations, the impact of photon absorption by iron is relevant and needs to be corrected. The iron spikes can be used to determine empirical influence coefficients for iron absorption of the higher elements of interest. It is state-of-the-art to use Lachance trail type correction algorithms. With the algorithm, the polynomial zirconium net count curve, which exhibits increasing photon absorption with increasing iron abundance, is converted into a straight line parallel to the x-axis. The numerical value is empirically determined and is setting and software specific. The scatter peaks are also impacted. In our case, the influence coefficient of the Compton scatter for iron absorption is 1, and that of the discriminative trace elements slightly differ from this value, which is an argument to use individual correction terms rather than to rely on a generalized matrix correction by just normalizing to the Compton scatter. It is evident that the determination of such empirical correction coefficients depends on a concentration series and cannot be performed with normal reference standards, because there are no geochemical standards other than spiked ones, which differ in just one element and are constant in all others. There's only one element of interest in pottery analysis which is enhanced by iron, namely titanium. The iron spikes are used to determine an empirical correction term to compensate for the enhancement of titanium. as shown before, the fundamental parameter software of the Delta instrument did not correct for iron enhancement. Part of the complexity of XRF spectra is the number of photon peaks with different energy levels raised by many elements, in particular the overlap of the K-beta peak of one element with the K-alpha peak of the next but one element, which is called spectral interference. Fundamental parameter calibration typically corrects for the respective overreporting of the next but one element, but not necessarily for all relevant elements under evaluation. The correction is made purely arithmetically based on the physically fixed ratios of the K-alpha and K-beta peaks, but we need to check whether our elements of interest are included in the interference correction. Here's an example of a missing or false interference correction of the rubidium K-beta overlay by the yttrium K-alpha peak, with the yttrium K-alpha peak. With increasing rubidium concentrations in the spike samples, the reported yttrium net counts decrease. In the example, the correction of the underreported yttrium net counts is as follows. The rubidium K-alpha and K-beta peaks have a fixed ratio empirically determined as the rubidium K-beta equaling to 18% of the rubidium K-alpha net count. The net area under the overlaid yttrium peak can be determined as region of interest from 14.6 to 15.3 keV. The subtraction of the respective yttrium K-alpha value times 0.818 from the respective region of interest then provides the interference-corrected yttrium K-alpha net counts. Yttrium itself causes peak overlap with niobium, namely the yttrium K-beta peak with niobium K-alpha. In this case, the deconvolution software ATAC7 overreports the niobium counts with increasing yttrium counts, which can be corrected with the respective empirically determined influence coefficient. As mentioned before, the Compton scatter is typically used in fundamental parameter calibrations for rationing or normalization of all other net counts. The Compton and the Rayleigh scatter are two instrument-specific photon peaks. They are scatter peaks caused by the tube metal in the sample. Thereby, the Rayleigh scatter behaves like the element peak of the tube metal, in many brands a rhodium tube, and the Rayleigh scatter then looks, so to speak, as if there is rhodium in the sample. The Compton scatter photons have lower energy than the tube element and are positioned left of the Rayleigh peak. The Compton peak is rather broad and quite unspecific, whereas the Rayleigh scatter is directly proportional to the current, the lifetime, and the window coverage, and is therefore highly appropriate for normalizing spectra. The Rayleigh peak indeed behaves like a regular element peak and is subject to ion adsorption as well as matrix and density effects of the sample, very similar to the mid-Z elements. Rhodium is a preferential tube element because the Compton and the Rayleigh scatter of rhodium do not interfere with the mid-Z elements, but are closest and most similar to them. Before normalizing with the Rayleigh scatter in a clay matrix, the Rayleigh net counts need to be corrected for ion absorption as well, although the influence coefficient is small. What, however, is even more important is distance correction with the Rayleigh scatter. Photon intensity decreases by the square of the distance of the sample from the detector. In non-destructive XRF analysis of pottery sherds, distance differences and surface irregularities are ubiquitous. Here, the decrease of the zirconium and of the Rayleigh net counts with increasing distance of the sample from the instrument window is shown. Ratioing the zirconium net counts with the Rayleigh net counts corrects the zirconium values over a broad distance range. Nevertheless, samples should be positioned as close as possible to the window, since any arithmetic correction adds additional uncertainty. As mentioned before, the Rayleigh scatter, like any other element photos, is impacted by several parameters, and measurement conditions should therefore be as identical as possible. The basics of the calibration approach with spike-fired clay samples have been published in 2016. The calibration factors empirically determined for the 8 discriminative elements in the clay matrix, as well as the element-specific absorption, enhancement, and interference coefficients, can be combined into a single term per element, with which the net counts need to be multiplied. A simple template in Excel was built which multiplies the net counts imported from the deconvolution program with each calibration term providing the weight concentrations in % or ppm. The conversion of net counts from hundreds of analyses into weight concentrations is then performed in the single copy and paste step. The spiking sets can also be used for validating empirical and fundamental parameter calibrations provided by the manufacturers. It is then up to the user to decide about his or her level of satisfaction. Data must fit for purpose. Many research tasks do not need accuracy, but consistency of semi-quantitative data may be sufficient. Other research tasks definitely depend on accuracy, and ceramic provenancing is a very prominent case. This is the end of part 1, and we may take some time for your immediate responses.
Thank you. Is there any questions before we go to the second part? Because we in the second part we shall follow a more detailed discussion on both parts. But now on the calibration, is anyone who would like to ask a question? I would like to ask you about the matrix effect. Are you calculating the average atomic number of each sample?
No. PXRF and powder EDXRF are, so to speak, absolute measures which need the calibration. And I'm not quite sure what you precisely wanted.
The effect of different atomic number, average atomic number of the material Z. How this is taken into account in the calibration?
No, the spiking concentrations are calculated from the in weights, and the loss of weight, the weight loss by the firing at 800 to 850 centigrades.
Yes, this takes out the humidity, so the water.
Yes, exactly.
Okay, I understand that. But about the other elements, the amount of calcium, for example, which
take zirconium. It is an absolute measurement of zirconium photons in that matrix, and it is important that the matrix is as similar as possible to the calibration standards. Yeah, for instance, if you want to extend your trace element concentration range and use, for instance, flying ash, which is particularly high in trace elements, you cannot use the calibration factors afterwards, because the matrix of the flying ash is completely different compared to aluminum silicate matrix.
Yes.
Yeah, but otherwise, the major elements do not impact the mode of quantification. This is different when you want to perform a total analysis, as is done in geology, where geochemical analysis intends on quantifying mainly the major elements, and the trace elements are not as important. And the major elements are then all calculated as oxides in order to come up to 100%.
Yeah. Usually, how many elements we are using for the provenance of ceramics?
Eight elements. 8 elements. Yeah, and the same 8 elements which are also used for obsidian provenancing.
Obsidian.
Yeah, this is by the end of the day, the volcanic glass is rather similar to clays and also to basalts. Of course, the composition in detail differs, but the amount of the sum of oxygen, aluminum, and silicon is rather similar, and this is what makes up the matrix, namely the absorption of photons of the other elements.
Yes. Thank you. Any question? No. Well, you can go on to the second part.
Okay. In the following, I like to present 2 cases of compositional analysis which go beyond the obvious primary task of ceramic provenancing, namely elucidating the procurement and trade of utilitarian as well as specialty pottery in the archaeological record. Before starting, I want to mention that I routinely use the exploratory graphics program GGOBI for data evaluation. GGOBI is an academic freeware based on R. It provides regular biplots and principal component analysis. But I use PCA only for initial orientation. Rather, I prefer the multidimensional rotation function of GGOBI. I'm a mere user of the program, but enjoy its graphic flexibility and transparency, so to speak, because even in the multidimensional rotation, the original data points are just visualized in the space, but without compiling new vectors or factors, which depend on algorithms which the ordinary user is often unable to grasp. Of course, visual data evaluation comes with some risk of individual bias from the observer. As an example, I take ceramic settlement analysis in the Rhine-Main region south of Frankfurt. Here is Frankfurt Airport, where we probably all have been before. From this greater region, I have analyzed some 7,000 shells and vessels as part of projects of the local archaeologists. I want to mention particularly the doctoral thesis of Eika Diesch at the University of Bamberg on the Church of Oberwoden, which is considered to be based on a small Benedictine abbey founded in the second half of the 8th. As part of her thesis alone, studied some 5,000 shells from the local museum collections, including the Archaeological Museum of the city of Frankfurt. The confirmation to get access to the material, most of which was generously lent out to us. There are two major regional wears, the so-called South Hesse mica wears, which were stratigraphically dated from the 9th to the 13th century by the Frankfurt town archaeologist Otto Stamm in the late 1950s. The coarse mica wear is obviously tempered. You see the large mica flakes here, because a clay deposit with coarse quartz sand and coarse mica admixture in a size sufficient for mass production over several centuries is highly unlikely. The coarse pottery was probably a desired cooking ware in the region, as can also be inferred from the many lid fragments which were found. Additionally, stove tiles have been recovered. Here, a 4-angular stove tile. The second regional mica ware is the so-called South Hesse fine-painted mica ware, a thin-walled tableware with larger regional distribution than the coarse ware, namely upstream the River Rhine up to medieval Basel. In addition, rim-painted beaker formed stove tiles have been found, and really exceptional roof tiles, some of them with reddish-brown painting. The painted roof tiles were found in the devastated water castle of Hainhausen, that means in a high medieval elite building. When we started the project in March 2020, the production sites of the coarse mica ware were unknown, but the provenance of the fine-painted mica ware was attributed to the city of Seligenstadt at the left banks of the River Main, however, only documented by a single kiln find. The biplot covers the respective mica sherds from the entire region. The coarse mica ware forms a single cluster. I call it a Tor cluster because without waste material, all ellipses are hand-drawn, not being calculated, but shown for better visualization of the clusters. The fine-painted mica ware forms one large and one smaller clusters. There's no particular abundance in any of the fine places, which would allow for narrowing the workshop location or to speculate about one or two different production sites for the fine mica ware 1 and 2. Now, what about the kiln and its immediate surroundings in Seligenstadt, which has been published by Karl Nahrgang, the regional cultural heritage responsible, in 1957. Nahrgang published several papers describing a pottery kiln with Pinkstoff ware at Seligenstadt. Pinkstoff ware was meant for yellow-painted earthenware, similar to the material found at the type location in Pinkstoff at the Cologne-Bonn promontory. Nahrgang further explained that the kiln fill is indistinguishable from the typical fine-painted mica ware found in the greater region, and he concluded that Seligenstadt must be its provenance. Since then, Seligenstadt was generally considered as the origin of the South Hesse fine-painted mica ware. When we started the study in 2020, we were, of course, highly interested to include the Seligenstadt kiln find into our regional analysis. However, the kiln find had disappeared in the Seligenstadt Museum, and it took Eika Diesch a full year until March 21 to search for and finally discover Nahrgang's boxes with the original material and the descriptions. The results were surprising. The Seligenstadt kiln find and the excavations by Nahrgang on the adjacent properties revealed two new clusters, Seligenstadt kiln 1 pattern and Seligenstadt kiln 2 pattern, clearly distinct from the bulk of find material in the South Hesse region, as well as from other excavation sites in the city of Seligenstadt. Nahrgang's Seligenstadt kiln must therefore be considered as a local production site with rather short operation and very narrow distribution, whereas the main production sites in South Hesse are still unknown. Though we detected a clay deposit which fits into the main cluster of the South Hesse fine-painted mica, where only waste material will finally confirm the location of the former workshop area. The second example is also from the region, pottery produced at Dieburg. Dieburg was a Roman civitas capital, and local Roman pottery is estimated between 125 and 260 AD, when the limes got lost as a frontier to the Germanic tribes. The medieval town of Dieburg got citylines around 1200, and a sizable potting district was excavated in the northern suburb of the town since the late 1980s. The Vesta finds were dated between 1330 and 1600. Thus, there is a hiatus from the middle of the 3rd to the early 14th century, where local pottery production is unknown. The Dieburg scherds exhibit two clusters, one cluster with normal zirconium and niobium values, and a second cluster with enhanced concentrations of these two trace elements, which are characteristic of the stable heavy mineral zircon and of the titanium oxides. Indeed, we could demonstrate that the clay pits are located in the western forest of the town, and that the clay sediments with the zirconium and niobium anomaly share this characteristic with published data of tephras in a nearby volcanic dome. In the graph on the right, the late medieval and the Roman pottery is plotted together. Obviously, the Roman potters used the same clay digging area as the medieval craftsmen. It is important to recognize that the low niobium cluster is mostly red firing, whereas the high niobium is low in iron and thus white firing up to about 900 centigrade. Therefore, the potters were in a position to distinguish between the two clay qualities, regardless of the difference in genesis and trace element content. As part of our regional settlement analysis, we had also access to the study collection of medieval pottery found by Otto Stamm in excavations of the 1950s in Frankfurt and deposited in the Archaeological Museum of the city. Stamm's study collection contains a group 21, which is called Pinkstoff type ware, made with clay from the Dieburg region. He dated the scherds stratigraphically from the early 10th to the 12th century. The clay specification of Group 21 was provided by the mineralogist Joseph Frechen from the University of Bonn of petrography of thin sections. Stamm's designation of Group 21 as painted pottery in the Pinkstoff style is convincing. The scherds indeed look like authentic Pinkstoff ware. The typical Pinkstoff vessel form is a spouted pitcher or amphora, probably used for serving wine. Stamm's Group 21, dated before 1200 and supposedly made of a Dieburg type clay, attracted our special interest because it may have extended the phase of local pottery production in the surroundings of Dieburg prior to the foundation of the medieval city around 1200. Thus, I have plotted Stamm's Group 21, the pink dots, together with the Pinkstoff Vesta cluster and the two known Dieburg clusters. Here, only the late medieval and early modern Vesta material from the Dieburg workshop district. The Pingstorff cluster strongly varies in the zirconium values, which, however, is confirmed by clay samples taken uphill of the old Pingstorff village and the cemetery where most waster pits and heaps had been found. Comes group 21 clusters together with the Pingstorff samples, and there's a strong overlap with the Dieburg low niobium cluster. By contrast, there's no Frankfurt shirt clustering in the high niobium ellipse. The PCA plot separates the Dieburg high niobium cluster, but is not in a position to separate Pingstorff, Dieburg low niobium, and the Frankfurt group 21. Since there are no Frankfurt shirts in the high niobium cluster of Dieburg, I have shadowed and excluded these data sets. The remaining 3 shirt assemblages still strongly overlap in the zirconium niobium biplot, nor is the PCA in a position to separate the groups. I have then rotated the clouds in the 8-dimensional space of the 8 discriminative elements and stopped the rotation whenever black dots of Dieburg low niobium pattern were clearly separated from the Pingstorff cluster. Those dots were shadowed and excluded. Since Pingstorff and Dieburg low niobium are obviously very similar in many positions in the space, it took me several rotation routes to isolate and remove all black dots. Finally, the Pingstorff cluster remained with all shirts of the Frankfurt group 21. Subsequently, I have rotated the Pingstorff cluster and searched for any group 21 dots which left the actual Pingstorff cluster. These dots, which differ in at least one position in the 8-dimensional space from the Pingstorff pattern, were then marked as open pink squares. The plot contains some double measurements of the same shirt. Thus, the number of open squares is larger than the number of clear outliers. After determining the shirts which are indistinguishable and thus identical in discriminative element pattern with Pingstorff, I additionally checked whether group 21 can be completely separated from the Dieburg low niobium cluster, which is the case. Now, what is the conclusion? Otto Stamm took the advice from the mineralogist that the group 21 shirts, which essentially look like Pingstorff shirts, are made with clay from the Dieburg region. Geochemical analysis reveals that the group 21 shirts, except for 5 outliers, are inseparable from Pingstorff waster material. Does this prove that these shirts were made in Pingstorff? No, this is very likely. These shirts look like Pingstorff wear, and they are geochemically identical with the Pingstorff cluster, and they definitely do not fit with either 2 known Dieburg clusters. However, we cannot exclude that there is still an unknown clay deposit in the surroundings of Dieburg, which accidentally exactly fits with the Pingstorff pattern. This is very unlikely, and Pingstorff is indeed a very plausible provenance hypothesis for the Frankfurt group 21. Now, what about the outliers? In the immediate neighborhood of Pingstorff, there are at least 3 other villages also providing Pingstorff-style painted earthenware. They slightly differ from the Pingstorff pattern. I have checked these clusters by rotating them with the 5 outliers, but there was no better fit than with the Pingstorff pattern. Therefore, the best actual explanation is that the Pingstorff waster cluster, though very large in sample number, is perhaps still not fully representative of the total variation of the site. Nevertheless, I consider the 5 outliers as unknowns since they are not identical with the Pingstorff cluster. The qualitative inference from studying the Frankfurt Group 21 is that the mineralogist who did the petrographic analysis in the late 1950s was probably wrong in attributing this set of scherts to a suspected Dieburg region claim. We do not know his arguments because his lab notes are not available. They have been archived, but nobody knows where. The fact that Pinkstoff tableware was transported upstream to Frankfurt is of no surprise. This was the most renowned tableware at this time before the invention of stoneware. We could identify scherts with Pinkstoff element pattern also at the Imperial Palace in Ingelheim, in medieval Worms, and recently in medieval Basel. Thus, the important result of studying Stamm's Frankfurt Group 21 is not that it is likely of Pinkstoff provenance and imported by Frankfurt upper-class citizens, but that Group 21 is not an index of a so far unknown early Dieburg pottery production dating prior to the city foundation around 1200. This is the archaeological result. These were two examples of non-destructive XRF analysis with results beyond just provenance determination. But there are also cases where known laser assemblages are almost indistinguishable with the 8 discriminative elements quantified by XRF, and unknown scherts and vessels can thus not be attributed to a specific production site. This situation is often found when pottery was made with poorly weathered clays and loams, as they are typical for the climatic conditions of the Quaternary. These plastic sediments are often low in content of stable heavy minerals and thus low in titanium, yttrium, zirconium, and niobium concentrations, which are essential for XRF provenancing of ceramics. In addition, there are sometimes highly unfavorable sedimentation conditions. Imagine such a clayey river may flood a delta of several hundred kilometers of length and width with such a well-mixed suspension. The chance to separate potting sites even on a distance of 50 to 100 kilometers is then rather small. This is the situation in the lower Rhine basin, where for a certain time period in the Quaternary, Meuse and Rhine flooded the lowlands and left red-firing, almost indistinguishable clay and loam sediments. There are many villages where modern lead-glazed tableware and decorated plates have been produced. Some of them can be separated, others cluster together in whatever position in the multi-dimensional space. These are examples of decorated plates dating from the 17th to the 19th century. In order to improve the visual impression of the decoration, the reddish paste often got a kaolinitic slip before the design was applied with the brush or the slip trailer. Under the lead glaze, the mineral pigments can be qualitatively analyzed, but not the paste. Unfortunately, even the non-glazed parts of the scherts and vessels are often contaminated with lead from the firing process. Lowest lead values are typically found on the existing broken edges, but even there, lead absorption and interference need to be corrected. The methodological approaches which I have presented concerning calibration, validation, and data processing have in common that I have full control on each step and I am not forced to rely on any black box operation. At the beginning, I thought this was important in order to overcome the skeptics and the criticism in the scene. Even nowadays, I have no problem with the many manual operations. However, I agree that most steps, with or without improved factory calibrations, can be integrated into a larger machine learning program and be fully automated. But matrix-specific will always stay a manual step. Valuable and innovative results will only be achieved when archaeologists and archaeometrists work closely together. There's an interface where interdisciplinary knowledge is required. That means the disciplines need to teach each other on the job. This is why sciences need to meet arts and vice versa. Thank you very much for your attention.
Thank you very much for the illuminating lecture. It was fantastically, tied, the first part of calibration and then the applications, which of course are founded on the calibration. Otherwise, our data without any meaning. And thank you very much indeed. It was well received, I think. And I would like to ask any questions from the participants. You can raise hand, or you can put the reaction here. Keelie, you?
Yes, you mentioned towards the end that maybe there are some opportunities for like AI integration of some of the calibration factors that you were talking about. So I was wondering if you thought that there was still always going to be a need for archaeometrists to be able to sort of look at the spectra and still be able to sort of tell the AI or interact with that AI and be looking at the spectra to really be sure that it's giving you sort of the right information at the end.
Well, checking the spectra is always important and useful, because you detect eventually you detect peaks which have not been included in the deconvolution setting. What I mean with machine learning is the work of Lee Drake, who got some advantage in a standard-free calibration. I think it could be a topic of an upcoming workshop to put all these tools and measures together, both for improving and further developing such automated systems, as well as to check them, to validate them. Yeah, both is necessary. And the basic critique in 2010, 2011 was that the development of the handheld instruments persuaded the users in archaeology for point and shoot operation of the instrument, and this critique was justified. There's no problem to rely on semi-quantitative or qualitative results, but you must know when this is appropriate and when it is not sufficient. And you must be sure that even your qualitative results are correct. That means that you do not mistake element peaks or something like that. Yeah, that means there is a basic methodological understanding which cannot be avoided and cannot be replaced. And this is still actual, even in 2025. This is still actual. There, when you attend international conferences and poster exhibitions, you always find presentations where you get the impression, well, did the scholar really understand what he or she did? And this is therefore, I highly appreciate the network because even with these many instruments which are used worldwide, there is still a lack of methodological understanding, and there is still room for improvement. And perhaps we can provide this improvement as part of the collaboration within the network.
Indeed. But I'm sure that the AI will play a greater role, you know, in the standardization and corrections and material type. I suppose, you know, the deep learning will take into account all these things.
Yeah. In facilitating, it is facilitating individual operations and can put them together.
Exactly. Yeah. Yes. Somebody, Kidan.
Yes, thank you for the interesting presentations. I have some questions from the two parts.
Yeah.
The first one is regarding the standard addition method. And there you need to inject a known concentration and prepare the different aliquots. So I wonder how you ensured homogeneity in the sample, and what's also the relevance of standard addition when it comes to PA-XRF analysis, because we want to do it non-destructively.
Yeah. But the standard addition procedure is just for calibration, not for sample measurement. That means this is just for the calibration of the instrument. And the clay blocks are fired. That means they have the same consistency like the sample material after. And
sorry, continue.
Yeah, and the crucial point in the preparation of the spikes is indeed the mixing. And when I first presented my results in 2014, the immediate comments were, "Oh, this is great, but it's so difficult to achieve homogeneity." And this is indeed difficult. And therefore, I told you that I check the entire batch, sample by sample, and if I recognize a single outlier, too much or not enough, then I have to discard the entire batch, and that happened. At the beginning, that happened. I had to discard entire batches. That means one concentration. And it also took me some time to learn which salts or compositions of the trace elements are useful. For instance, in case of niobium and strontium, only the oxides work, not the chlorides. Yeah, the chlorides are much too mobile. During the drying of the clay, the salts, the chlorides move to the surface, and you have then an overconcentration at the surface. That means for technical reasons or for chemical reasons, the mobility of the salts, you get an inhomogeneous product. But when you switch to the oxides, the mobility is much lower, and I was able to produce homogeneous batches. Each batch around 1 kilogram. That means the spiking concentration is calculated. The spike is, let's say, 220 milligrams in 1 kilogram, and then you calculate the final concentration. And if you make a weighing mistake, then you lose the quality of your coefficient of determination. Yeah, therefore you have a good measure of control.
And you use mixer for homogeneity.
Yes, but yes, I use a mixer, and it is very laborious. Yeah, that means I started with small quantities of 100 grams of clay powder, and then your aliquots, which you have to weigh, are also smaller, and you increase the weighing error. And 1 kilogram of clay is a good optimum, is a good compromise for handling the pace, as well as having a good quality of weighing. And in industry, there is some knowledge how to mix small amounts in a large batch. That means you need to start with an aliquot of the large batch, and first mix it into the aliquot, and then you go to the next aliquot, and finally to the entire batch. And even the entire batch you need to stir for, let's say, an hour. Yeah, you imagine you want to homogeneously distribute 100 milligram of yttrium whatsoever in 1 kilogram, 100 milligram in 1 kilogram, and it shall be absolutely homogeneous. Otherwise, you can discard. You must discard the batch, and this is what the others have also experienced. Yeah, and when you try that 2 or 3 or 4 times, then you lose, then you give up. Yeah, and in my case, I didn't want to give up, because my intention was to demonstrate whether it is possible to do ceramic provenancing with a non-destructive instrument or method. And the critique by Keelie and Speakman was exactly the calibration. Therefore, I started with calibration. The first thing I did with my first Bruker in 2011 was not to measure shells, but to calibrate and to validate the instrument. And I failed to validate it. And it wasn't the failure of the company, but it was simply that the reference materials which I had acquired, I had acquired 20 reference materials, each for, let's say, 100 to 200 USD. And the regression line was a dot cloud. Yeah, the validation simply didn't work.
Yeah.
Okay.
Also, we must not forget that the PXRF is a surface analysis, and in real cases in ceramics, in buried ceramics, we have the phenomenon of leaching or enrichment, which is not observed, is not present in the briquettes, which are made today.
But this is a separate issue. And in the STAR paper, we have addressed this issue, namely, is there inhomogeneity which contradicts a non-destructive surface analysis? But the advantage of XRF in contrast to pixel, is that for the mid-Z elements, you have a deep measurement area of up to 6 to 8 millimeters. That means only the low Z elements, namely sodium, magnesium, aluminum, and silicon, are pure or more surface measurements. And for instance, there is a phenomenon that whenever you have a paste with fine or coarse quartz sand in the paste, you inevitably underestimate the silicon content by non-destructive analysis. That means if you perform a non-destructive analysis of pottery, you cannot quantify silicon because you cannot, you get no photons from silicon below the immediate surface of the sample. This is the reason, this is one of the reasons why it doesn't make sense to quantify aluminum and silicon. The other reason is that in pottery, these two elements are not really discriminative because the concentration range is too narrow in pottery. And, but for the other elements, even gallium as a proxy of aluminum, up to niobium, you have a deep entry measurements because not because of the X-ray. The X-ray goes through the wall. That is the reason we need the lead cover. But the point is that from gallium to niobium, the excited photons go through several millimeters of sample and reach the detector. And what we do with PXRF calibration is that we calibrate for this complex setting. That means the calibration is, let's say, the same for non-destructive and pressed pellet analysis, but in pressed pellet you have homogeneity, and in non-destructive analysis you don't have homogeneity. But you can overcome this problem by simply taking several shots. That means if somebody says, I really want to know the average concentration of the discriminative elements without destruction, without powdering, then you must take 10 samples and do the average.
Yeah.
Yeah, but we have described that in this STAR paper, because this has been published in 2016. That means this was the hot phase, yeah, where we had no chance to convince the reviewers without addressing all these issues.
That's that. Okay.
Yeah.
Thank you. Yeah. Any other question?
Maybe if we have time, I have, some remaining I can ask.
Okay.
But I can give the chance for others if there is more.
Well, I don't see any other, so you can go on.
All right. So the second one is you said 8 elements are quite often used for provenance study of ceramics, like obsidians. So presumably this could be the trace elements like strontium, rubidium, yttrium, and the ones you mentioned here.
Exactly.
But why not the other elements, including the lighter ones, aluminum and silicon, if you use vacuum or inert gas atmosphere?
Yes, you can, as I said, you can measure sodium, magnesium, aluminum, and silicon under helium. I do that. You see the gas bottle
Yes.
in the background. Yeah, that means I routinely measure these elements under helium, but particularly for pottery, the discriminative value of aluminum and silicon is very low. It's very low. If you plot aluminum versus silicon, even if you suggest that the silicon values are correct, which they are not, you will find a scatter and an overlap of clusters, which is of really no discriminative value. Yeah, and this is the same with obsidians. In obsidians, you typically have something between 90 and 95% silicon and traces of aluminum. That means it may make sense to determine the aluminum traces, but the silicon value in obsidian is, to the best of my knowledge, of no discriminative value at all. Yeah, because all obsidians have more or less the same silicon value, more or less.
Right. Yeah, but
Yeah.
for that case, it's clear. It's glass, so silicon could not be used for that purpose. But in case of pottery, you can have aggregates, very fine and coarse ones at times. And they can be diverse aluminosilicates, and that can lead to differentiation in the ratio of calcium to silicon and other elements like potassium, calcium, titanium, chromium, depending on...
Yeah, for the other elements, I agree with you. But in case of, I also agree that aluminum has some potential, namely as a measure of the plasticity of the paste. That means there are there's pottery with a high sand content and pottery with a very, very high aluminosilicate content. But the clay mineral itself always carries both aluminum and silicon, and this makes these two elements with these millions of clay pits and fabrics with or without temper makes this very, very similar. And even with the mid-Z elements, it is difficult to separate very similar clusters. And if you try this with aluminum and silicon, I think you can give up. There's no chance. And I do not know any paper which is successful there. I also have in mind a lot of provenancing work was initiated by geologists and geochemists, who are familiar with full geochemical analysis, including the low-Z elements as oxides. And when they started plotting aluminum and silicon, as far as I know, they rarely had any success. And I know concrete cases where the geochemist experienced with geological sources gave up and said, I cannot find any pattern here. And I took the published data and used the trace elements, and I found a pattern.
Okay, and the last one I have is the application, especially the one related to Schlingenstadt. There you have clusters of 3, one from Kiln 1, Kiln 2, and the third
Yeah.
one is fine mica 1. Is
Exactly.
that the same? Is that the same as from the 9th to the 13th century you mentioned earlier?
Exactly.
Okay. Okay.
Yeah, and all 3 clusters fall into this time span, but there's no exact dating so far. Yeah, the major cluster was the fine painted mica ware, which was visually undistinguishable for the archaeologist when he recovered the kiln find, and we could show that the kiln find consisted of 2 new trace element patterns which are distinct from the main cluster, which is distributed all over the region up to Basel, Switzerland.
All right. Thank you.
Yeah.
Thank you so much.
Thank you. I don't see anyone else. No, thank you very much once more. It was fantastic, I think the discussion. It is the core of the problem, the calibration, as everybody knows. And you presented, I think, a very clear picture of what is going on with provenance, specifically on ceramics, regarding calibration. And for this reason, I thank you very much, and I look forward to, if you like to submit any review paper as a review, your talk, we can process it in the proceedings of the European Academy of Science and Arts Journal, that it is online. I will give you details actually, if you have time and you would like, to present this as a review. You are most welcome, to submit. Okay, thank you once more, and thank you the participants. Thank you, Keelie, and hope you have all a nice week, a nice weekend, and summer holidays.